What up? It's your boy Juice. This is Shockwaves Part 1. That way I can give you the information and knowledge that I have to give to you. For health reasons, safety reasons, precautions, warnings, predestinations, for future destinations. Shockwaves Part 1. I've been saying there's booms. They're coming from both the ground, earthquakes, volcanoes, yada yada yada, and the sky. Compression, earth changes, planetary objects, so on and so forth. Has it been getting windy in your area? I bet it has. Have you been feeling like shit? I bet you have. Well, you need to be in a frequency that's with the earth. If you are not, this will throw you off. But there's also other things to take into consideration here. There's blasts happening, okay? Let us educate ourselves.
This week for EMN5, we're going to talk about blast injuries. And these injuries mostly come from a combination of the heat and the kinetic energy.
Heat and a kinetic energy. Kinetic energy with heat.
Caused by the chemical combustion. So let's talk through what happens when you have a blast. So first off, you get this blast overpressure.
Pressure.
Shockwave, basically kind of a blast of energy. Then you get a blast wind, which
Wind.
is a huge gust of air. And then lastly, you have this negative pressure. And
negative pressure.
It would look something like this. So first you have...
Pay attention to this graph she is showing you. This is pressure plus time. This is what we call sound pressure. Okay, this is how it's usually measured. I will take a measurement with my phone and show you. But for now, let us educate ourselves on how this works so that I can show you, because I can't use the mic and the program at the same time because it's listening to the sound pressure. Does this make sense? Let us continue.
This huge spike, that's your shock wave or blast overpressure. Then you have a blast wind, which is followed by this little bit of negative pressure dip. So a couple things you have to take into account when thinking about how much injury you might see from your blast is the distance from the blast and then what your surroundings are.
The distance and surroundings.
Matters a lot, actually. The blast energy decreases with a cubed root of the distance, which basically means if you're 10 feet away from the blast, you have 8 times more blast injury than if you're 20 feet away.
Yeah, so it's gonna blow up your fucking feet.
So next you have to think about what are your surroundings. So take, for example, an underwater blast. Do you think you'd have more or less injury from that? So you're actually going to have more injury. That's because water is incompressible. You're going to have a faster blast propagation and also a...
Let's take humidity and rain into consideration.
Lower dissipation of that energy. What about if you're in an enclosed space, like inside a room? This is a meth lab. So you're going to have more injury again. So let's go back to this graph we saw before. This is what it looks like in an open air explosion. And this is what it looks like in a closed space. So you can see this blast overpressure. This energy bounces around the room in an enclosed space and causes multiple of these blast pressure waves. It can result in a lot of injury. And same thing can happen even just next to one wall. Again, that energy bounces off the wall and comes back.
Circles. Look at the circles. It's circles.
And you end up with kind of twice the amount of blast. Now there's 4 types of blast injury categories. We have primary, which is from the blast shock wave or overpressure. Secondary, which is from flying debris. Tertiary, in which the victim themselves gets displaced. And then quaternary, which is kind of a miscellaneous category. And each of these categories can cause various different injuries. So let's start off with primary. I think it's one of the hardest to understand. So this primary injury is caused from the blast overpressure, that shock wave. And it mainly affects spaces in the body that have an air fluid interface. So for example, the ears, the lungs, the GI tract. And there's a couple different forces that work here.
Your head, your ears, your breathing, your stomach.
So for example, let's talk about the lungs. This has the interface of the capillaries and the alveoli as your air fluid interface. So first thing that happens is when the shock wave hits, you have this very dense, non-compressible vessel with the liquid inside right next to the alveoli, which has compressible, lower density air. And what happens is when that force hits, it displaces the vessel into the airspace, and it usually
It basically shakes you the fuck around. It's called the Law of Inertia. That's how they say Princess Diana died, because when she hit the wall head first in the car, she survived because she had her seatbelt on. But with the law of inertia, even though you come to a complete stop, your body continues to go. When that seatbelt stopped her body from being thrown out the windshield of the car, right? The law of inertia took place. That means her organs kept going. So they say that her heart went through her rib cage.
It ruptures the vessel and it compresses that air a lot. So then the second thing that happens is that you have this compressed air, which then explodes back outward again. And so this causes a couple things. It's going to probably rupture the membranes and it can cause a mixing. So you end up with blood leaking into the alveoli, which results in ARDS and acute lung injury. And you have air leaking into the vessel, which can cause air embolism. All right, next is the secondary, which is from flying debris. And this causes...
Just saying. Just saying.